one. Okay, so these are fatigue tests. Let me run this one again. I'm not sure if you can hear the sound on this. You don't really need to. It's just loud background noise. All right, so that's fatigue. These are fatigue tests. Not the most exciting test to watch, but fatigue itself is actually a really interesting topic. So let's go ahead and get into it. So what is fatigue? It's the failure due to cyclic loading, probably be the easiest definition. But the idea is you've got some kind of a microscopic flaw. It could be a crack, could be a scratch on the surface, could be a precipitate particle that's brittle, and so it cracks under stress, and now you've got a crack inside your material. And this flaw this crack will continue to grow very, very slowly through this fatigue process, the cyclic loading, and eventually it will reach the critical crack size that we've done in fracture mechanics, and you'll get failure. Okay, so this is showing a bolt head that cracked in brittle fracture. This region over here, you can see that's where the fatigue crack was growing. This would be at the bottom of one of these notches, right, where the stress has a higher intensity. And then once this reached the critical crack size here, the rest of the sample is just a fast fracture case. So types of cyclic loading. So there's three main types. We're only going to be concerned with one type here. We've got the low amplitude acoustic vibrations, and so we're not going to worry too much about those. They don't usually lead to fatigue problems. I want to jump to C now. C, we talk about low cycle fatigue. So low cycle meaning that it only takes a few back and forth cycles of fatigue. This would be like bending of a paperclip, right? You bend it forward and back, and only after a few of these cycles, you get fracture. Okay. So that's not usually all that interesting either, because in this case, you're loading above the yield strength, so you've already exceeded a design limit anyway, and then you get fracture. So really not the best example of fatigue, but it's the one that people use a lot to explain fatigue. But that's actually a different process than what we really mean by fatigue, which is high cycle fatigue. So in high cycle fatigue, you may have tens, hundreds of thousands, or millions of cycles before the sample suddenly and unexpectedly cracks in a brittle way. So that's what we're going to focus on. All right, so in fatigue, a structure might undergo a variety of cycles. There usually isn't just one sine wave frequency. Right? In terms of an airplane, you can imagine that there's a cruising type cycle of stress versus time. If the plane hits turbulence, it might be slightly different. During the takeoff and landing, you've got some very high stresses, but not very many cycles here. Where the ones when they were cruising or in turbulence, you've got a very long time frame, many, many cycles, but lower amplitude. And all of these result in damage to the sample. And so they really all have to be taken into account. All right, so, and it can be. We'll talk about in the next video, we'll go through an example of figuring out the lifetime of a sample that's undergoing fatigue. So first, let's take a look at some definitions for fatigue. So when we talk about fatigue, we talk about there being a mean stress, we talk about stress amplitude, and we talk about a delta stress. And so hopefully you can see them all defined here. The mean stress is just the average of the maximum stress and the minimum stress. And so that's your mean stress value. Your stress amplitude is just going to be the maximum stress minus the minimum stress divided by 2. Okay. There's your stress amplitude. And then, of course, that the delta sigma is just sigma max minus sigma min. Okay, So not only is the stress amplitude important, but also the mean value. Where are you overall in terms of the stress? And so one of the things that we can plot is a fatigue curve. And what we can plot here is the stress amplitude versus the number of cycles to fail. So this curve is produced by taking a look at the stress amplitude onto a sample, and then experimentally determining how many cycles it took for failure. Okay, so each of these, so what we would have really is a bunch of points on here representing different samples. Now, in some cases, this stress value might continue to drop, as in this one. This kind of implies, if we keep extrapolating, that even if we end up at very low stresses, we will still fail. There doesn't seem to be a limit on the stress to cause failure. But we're starting to get to cycles now that are well beyond the lifetime that we might be designing for. Now, that very much depends on the frequency of the cycles that it sees. But in these cases where there isn't a well-defined limit on the stress to cause fatigue, we like to use something called an endurance limit, and that's just defined as the number of cycles, it's defined as the stress at 10 to the 7 cycles, which for many applications is considered a long time, sufficient time. All right, so this is maybe a typical sample. This is an extensometer that's attached to the sample, so you can measure the crack opening displacement. But this is basically a tension machine, and we've got rods that fit through here, and then the sample is just pulled on, opened, and then closed, open and close with a small amplitude, cyclic amplitude. And on the sample itself, if you look real close, you can see that there are these little lines on here. These are all equally spaced, so that if you place a camera on this, you can watch how fast the crack grows with number of cycles. And that's the data that you really want off of this. You want to know the change in that crack length A versus the number of cycles of the test. So here's an example of a failure, a little bit more of a close-up. Generally, you can tell where the sample has failed from because there's always this region that's usually pretty bright and shiny. It may have marks. You may have to look real close to see them. But what these are marks where, and these would be much closer together than what I'm drawing, but these would represent changes in the crack position as it's moving out per cycle. And so what'll happen is eventually you'll get enough cycles to move this crack all the way out to the critical crack size. Once it meets the critical crack size for the given stress that's on this, the maximum stress of the cyclic wave, then you get fracture. You got fracture mechanics kicking in, and you've exceeded the stress intensity has exceeded the fracture toughness, and then you get rapid fracture. And that's what you're seeing here. So just the rapid fracture. So this whole part of the sample would have cracked within 1 cycle once you've reached the critical size. So up until the critical size, you really don't know anything's wrong with the sample. And then suddenly you get this catastrophic failure. Just another example showing the origin of the crack. Usually these lines kind of trace back to the origin. This is where the crack, again, ran through the sample really fast. And that crack, as the crack speed rises, the crack changes directions, and it can split. And it kind of results in these lines here that sort of point back to the origin. And if you look down in here, you can see that there are some inclusion particles. And these are usually, in many cases, these would, especially in a steel, this might be like an iron carbide inclusion particle, maybe a chrome carbide, something else that's very brittle. And so that was the origin of the initial flaw in the material. All right, so we saw the fatigue curve before looking like this bottom one, but for a lot of materials and some steels in particular, it will look like the top curve where you get to a certain number of cycles and then the curve levels off. So there's this fatigue limit. So this means that below this value, below this stress amplitude, okay, so we've used sigma sub A, there's no fatigue. So you don't have to worry about fatigue. Above that, then you've got to worry about whether this number of cycles here, this lifetime, is sufficient for the use case. And then again, if you have one with no fatigue limit, then you have to use some convenient measure, maybe 10 to the 7th, or maybe if this is a part that's going to see very high frequency cycles, you might need 10 to the 8th, 10 to the 9th cycles, and you can pull off your stress amplitude to cause failure there. So here's some real data. So the top one is a A517 steel, and you can see how this curve starts to tail off to a fatigue limit. We're already out to 10 to the 8th cycles here. So we've got 100 million cycles. And these last 3 points that are on here with the little arrows means that they haven't actually failed. The test stopped at this 100 million cycles, and the sample did not fail. So we don't know where they are, but it helps us, though, to still define this fatigue limit. So on this particular sample, if we have stress amplitudes below 414, then we don't have to worry about fatigue. All right, and then on this, now, I should be a little bit careful here because also in these tests, there is a mean stress that's used is going to be 0. And that's what we've got here. This is sigma sub m mean equals 0. Right? So that means that the maximum stress is equal to the negative of the minimum stress. So it's plus or minus, say, let's see, stress plus or minus 500 megapascals, for example, is the applied state. Now, if you were to increase the mean stress, so instead of having, right, this case here about 0, if you increase the mean stress, so maybe you're here, but your stress amplitude is still the same, say at 500. Well, now this maximum is not 500 anymore, right? It's 500 plus the mean value. So this is a much worse case because you're actually applying a maximum stress much higher. So that's going to have a much shorter lifetime. So you do have to specify on these curves what the mean stress value is. All right, and then here's your aluminum sample, 7075. And you can see that this doesn't appear to have a stress limit, fatigue limit, sorry. All right, another one of those curves where we've got multiple things on one plot, and we said that we want to be able to understand what concept that this plot is trying to show us. Okay, so this plot is a matter of having different mean stress values, and we want to see what happens to the overall fatigue curve. So let's go ahead and just get rid of these, pretend they're not there, pretend we don't know anything about this. And we want to know which one of these curves has the highest mean stress and which one's the lowest mean stress. All right, so what we can do is let's go ahead and fix the stress amplitude. So I'm just going to pick some value here that goes through all 3 curves. Okay, I know that line's not horizontal, but that's okay for what we're doing here. So we're going to go ahead and pick a constant stress amplitude. So I'm going to let that be a constant. And then what I'm going to do is take a look at the intersection of each of these curves, and this will tell me the number of cycles to failure. Okay. So my sample here has a large number of cycles, or a large lifetime, and the one over here has the shortest lifetime. So if I have a sample that's got the shortest lifetime, it has to be one that has the worst, the most damaging stress conditions on it. So that means the highest mean stress value. So this would be my highest mean stress. And then likewise, this curve over here that has a very long lifetime must have the lowest mean stress. Right? I mean, ideally, if you got the mean stress value into compression, far enough into compression where the maximum stress on the sample was still in compression, then you won't have your crack opening at all. And so at that point, you'd have no fatigue. So that's kind of the limit you can think of to think about what this mean stress is doing. All right, so let's see how we did. So this picture says that sigma mean 3 is greater than 2 is greater than 1. And that's what we said. Highest mean stress, lowest mean stress. All right, so that's how you want to, again, reason out these curves. That's what it's trying to show you. So the higher the mean stress, just to make sure this was a clear, the higher the mean stress, assuming a constant amplitude, right, that's important, then the shorter the lifetime. Okay, the sample fails quicker. Okay, so next time we're going to go through and take a look at the crack growth rate as a function of the number of cycles, and we'll use this to be able to make predictions for a sample under cyclic loading for its lifetime or number of cycles to failure. So we'll save that for next time, and we'll go through an example problem as well.